Yes, we can hear you, sir.
Okay, good.
Can
Okay,
hear
that's
you.
good.
Good evening.
Okay, okay.
Your
All
screen,
right.
your screen is not clear.
It's not clear. Okay, okay. I'll do that now. I'll make it clear now. Okay. So we'll just wait a little bit for more people to join us before we get started. Okay. Okay. Okay.
Before while we were waiting, can one ask a question?
Yeah, if it's from the previous class, if it's before the feature scaling. So the questions
Yes.
can come actually, yes, if it's from everything I thought, because I'm going to continue the class today. Of sure, so you can ask any question
All right, thank you, sir.
while we are waiting.
When you talk about how to know if the machine learning has taken place, you made mention of mean square error, and then you talked about
Yes.
regression, but you didn't explain the regression. You mentioned the regression that once the value is closer to 1, it means that the learning has taken place or something like that. But please, can you expand more on the regression value?
Okay, on the mean squared error,
No, not the mean square, the
right?
regression itself, the regression. The
Oh yeah,
regression
we haven't
analysis.
really, yes, we have not really touched that, what regression is specifically.
Okay, we are still
We
going
have
to
not
get there. All
actually,
right.
yes, we
All
are still
right.
going
All
to
right.
talk about what regression is and how does regression help? How is
All right.
regression related to machine learning? That one is
All
still
right.
down the lecture.
It's all right. I'm fine. Thank you very much.
Okay. So just wait a little bit for more people to join us. Okay, I think we should just start now. So before we start, let me just make this my screen. I don't know, is my screen clear? What you're seeing on the screen right now, is it sharp?
Well,
Not
for me,
really, sir.
I think I can see
It's
it.
not sharp.
Not as sharp as the one
It's,
we
it's,
used last.
it's quite good.
For
But
me,
it's clear.
Maybe you can increase it.
it's quite blurry. Okay, I'm coming. Okay. Okay. What about now? Is it better now? The screen.
Yes, it's better now.
Okay, good, good. So now we get started. Now, let's just do a little recap from our previous class. The things that we learned from the previous class. We did a little introduction about what machine learning is all about and what is machine learning, how it can learn from the environment because it's a machine. It doesn't see life the way other living people living things see live or view lives. So we have to convert most of the data from the world. We have to convert the data, the information from real world to a format that a machine can understand. That is numbers. Everything a machine does is just calculations. So we need to convert things. We need to break things down in numerical form before a machine can actually understand. And then we talked about intelligence, the definition of intelligence and what is learning, and then the learns from the data set. The data set is the word of a machine. Although from the previous class, we didn't actually show an example of a data set. So today we are going to show some example of a data set so that we can have a very clear view. What we just showed now is this diagram here on the screen. We showed X and Y. This one here, this entire one here is representing the data sets. And then we talked about the classification, the different types of machine learning, supervised machine learning and unsupervised machine learning. Then the focus for today is regression, and we gave an example of how we can predict the number of ice cream being sold as just an example, considering the temperature and the day of the month. Then we talked about what supervised learning really is. And then featureization, we talked about the steps in featureization, data collection, data cleaning, data transformation. And that was where we stopped. The last, if I recall clearly, we talked about one-hot encoding and label encoding. One-hot encoding is using 100 to represent something, maybe red, 010 to represent green, and 001 to represent blue for one-hot encoding. So this is what the computer sees every time it sees blue. This is what the computer sees every time you're talking about green. This is what the computer sees every time you're talking about red. And then we talked about feature scaling. Now, okay, your feature scaling is where we want to continue. Now, if you recall, I said that it's always a good idea for all your data to be within a scale of measurements. Now, what I really meant is this. Let me show you a particular data set. So I'm going to share this window now. So this is just a dummy. This is not a real data. The data I'm about to show now is not real. It's just for this training purpose. Just for training purpose. I'm trying to share the screen, but it's just disappearing. Okay. Can you see the data sets?
No, it's not showing yet.
Can you see the Excel spread? Not yet. Okay.
Not yet.
Okay,
We
good.
can't see.
Okay.
Not yet.
Okay, what about now?
Not yet.
No, still not showing.
It's still
Yes,
not
it's
showing
showing now.
now.
It's showing now.
Okay, good. So yeah, good. So now this is an example of a data set. Okay, so now remember I talked about features. In the features that I'm referring to, as you can see in this data set, the data set is usually in a tabular form. Now, this number here is a feature, gender here is a feature, the name sets is a feature, title, given name, middle and initials, middle name, initials, the surname, all of these are the features that we are talking about. And when it comes to the actual thing that we are trying to predict, is usually at the last. What we are trying to predict is usually at the last. It will be something here, probably maybe on this last column will be maybe a purchase decision or not. Might be a purchase decision. A purchase decision could be either yes or no, or what was the amount of stuff that was being purchased by each individual. Now, what is on the row? So all of these are columns. So the features are, or they are all on the columns, and they are the things that are going to be used by the machine to make calculation if you are going to load it in the machine learning model itself. Now, for the role, all of these rows that you're seeing here, they represent the what? The data points. All of these rows represent the data points. That is, they are the individuals that we are trying to study. They might not be human individuals. Just depends on what you are studying. For instance, you might be studying flowers and you are collecting data on the different characteristics of flowers, probably the color of the flower, the size of the leaves, the height of the plants, the color of the fruits. So on each of these roles will not be the individual plants that you've collected the data from to study. It will be the individual plants, but in this case now we can see that they are humans. This would be the individual humans, and on the column side will now be where the features are. These are all the features there. Now, for a machine to actually understand this data set, if you are going to use everything on this data set, if you are going to use all the features, then you have to featureize the columns that do not have numbers in it, like gender. You have to featureize gender into male and female. You can featureize it as 0 and 1. You can use 0 for male and 1 for female. For the name set too, if the name is not something important, like the name set, if it doesn't contribute anything at all, the name set, now as you can see now, this one is just giving information about probably the origin of the person, where the person is from. So this doesn't really give so much information about, it doesn't really add any value to the machine. Title too doesn't add much value to it, unless it has something like doctor, maybe doctor, then Mrs. that probably is talking about the educational level of the person. Then that is now left for you to decide whether or not you want to add that title to it. Then we have the given name here. The name also doesn't really have much bearing for our analysis. The surname too doesn't have much bearing. Now look at this. Amount paid. Amount paid might be a very interesting data that we want to actually study. You can decide to select that. And you can just highlight this for now as one of the features that you're trying to select. You just highlight it. Then you can talk about probably the street address. Maybe people in certain area, or maybe people in certain locations, cities too, might actually be very important for you in your analysis. You can decide to highlight that also. Then the zip code, the zip code can say something about the location too. If that is important, you can put it there. You can look at the feedback too, all other things that are important. So now, talking about feature scaling, now I'm going to compare two things. Now I'm going to compare, let's say, zip code. For instance, look at this zip code column. You notice something. You notice that the values that we are finding in the amount paid is going in the tens thousands. Look at this one. This one is showing over 80,000 here. 13,000, 44,000, 64,000, 60, 98. You are already having an idea of the range of values to expect from this column alone. You're already having an idea. You can see it that is ranging from about 100,000 to maybe 1,000 and less. But the zip code is only ranging from what to what? It's only ranging from 1,000 to 9,000. It's not moving past 4 digits. So these two things cannot be easily compared together when we load it in our machine code. Let's say we are comparing these two these two features. We are loading these two features in our machine. We want to load the amount paid and also want to load the zip code. It's going to be advisable to make sure that the amount paid, the zip code, they are all within the same range of value. Now, that is what we are going to talk about. Now, there's a reason for this. Let me share this window. There's a reason why we need to do this. Now, this is it. Now, look at this. Let's say this y-axis now. This is normally the y-axis, but I'll call it x1. Then I'll call this axis xo. XO, X1. Good. Now, if you notice something, you will notice that this thing, these two, this XO and X1, they are not in the same range at all. X1 is quite wide, is really, really wide compared to X1, the one that is standing vertically, is very small. So if you are going to, if you notice that if you are going to calculate the slope, remember that the slope is the change in this vertical to the rate of change in horizontal. If you look at it, if you divide this small distance here by this small distance, by this larger distance, you are going to have a very small value at the end of the day. Let's say from here to here is let's say it's 2, for instance. From here to here is just 2. Why from here to here, it looks like it's about 7. So by the time you are trying to calculate the slope, it's going to be 2 divided by 7, which will give us a number that is less than 1, a very small number. The same thing is going to happen too. If assuming this side was quite long, I'm coming. The same thing is going to happen. Let me draw another graph. Now I'm going to make this very long, but it should be quite small along this. So you can see now the X1 now is quite long, but XO here, horizontal, is small. So if you are going to calculate the slope of this, let me input some data points there. And then we draw our regression line. This is it here. Let's say this is the perfect fitting. It doesn't really look perfect. This is the line that fits the points on this particular data sets. So if you are going to calculate the regression, the slope of this, you would notice that from year to year is going to be quite long than from year to year. Let me show you some. I'm coming. So from year to year is quite long compared to from year to year. And that is how a machine calculates the slope. By the time you divide this place by this place, you are going to have a quite large slope. So this is just to show you the effect of not scaling. The effect of not scaling. Let's say this part here is 5, and this part here is just 2. By the time you divide 5 divided by 2, you have a number that is greater than 1, about 2.5 or 1.5, as the case may be. So what this scaling is trying to tell us is that when features are not within the same range of value, the machine will assume that a feature is more important than the other. For this case, the machine will assume that this x0 here on the horizontal, it's more important than this x1 on the vertical, because of the ratios here that we have, because of the rate at which it is changing, because of the slope. Now, compared to this one, to the machine, we assume that this feature that is along this vertical axis, the XO, is more important than this feature along the horizontal axis, X1, because it's carrying 5 and this one is just carrying 2. So we have to make sure that everything is within the same range of value before we before we actually begin our analysis. So now I'm going to share this window again. I'll go back to this slide to share the window. Just a minute. Okay, good. Now we are back here. Now there are different ways you can scale. There are different methods for feature scaling. There's normalization and there's standardization. Yeah, those are the two major ways in which we can actually scale. Some people can scale by dividing everything in a particular feature by a particular number. Say now, you notice that in the last data set that we showed you, we saw a value of 88,000 there, and we saw a value of maybe 217 there. We can decide that, okay, we are going to divide everything by 1,000, so that 88,000 will become 8,800. It's going to be within the same range as the zip code that we're trying to compare it with. That's a method. That's just a very brute method for scaling. But we can also use normalization. Normalization just puts all the data points between 0 and 1. There's a mathematical formula for that. Standardization just centers all the data around the mean with a standard deviation of 1. Sometimes it's usually more than that. The standard deviation can be 3 also. B plus 1 plus 3 to minus 3. So that is what feature scaling is all about, just to make sure that all the features contribute equally to the analysis without putting too much emphasis on a particular feature than others. Now, for feature selection, feature selection is important in cases where we are considering a lot of things in our analysis. Like in the data set that I showed you, you saw the name there, you saw the son name there, you saw the middle name there, the location, the comment, you saw a lot of features there. Obviously, we cannot just load all of these features into our machine because there's a principle called garbage in, garbage out. Whatever you put into the model is what is going to come out. So if you put so much useless features into your model is going to be giving you useless results. So you need to be very selective about the things that you are feeding into your model, that you are using to train your model, so that your model will be able to give you relevant results. And that is where feature selection comes into play. Feature selection comes into play. Okay. Good. So now, to improve the model performance and reduce complexity, it's essential to select the most relevant features. You can use there's so many methods that you can use for feature selection. You can use principal component analysis for it, and you can also use recursive feature elimination and also correlation analysis. Now, let me explain this. For instance, this recursive feature elimination, recursive just means coming from behind. That is, you begin by eliminating features that are least important. The least important feature will be eliminated first. That's what recursive feature elimination is all about. For correlation analysis, this correlation analysis just compares every possible pair of feature to each other. That is, it compares maybe feature 1 with feature 2, compares feature 2 with feature 3, compares feature 3 with feature 4, compares feature 4 with feature 5, and then looks at how they are correlated, whether they are positively correlated, negatively correlated, or they have no correlation at all. That is what the correlation analysis is all about. Why the principal component analysis is a dimensionality reduction technique that is selecting based on is going to select the features that has the highest variance, because a feature with a higher variance is usually the one that is much more valuable. That is the principal component analysis. That's what it's all about. So now let's look at some examples of featureization now. Now let's consider a simple example of text data featureization. This is a raw data text, a raw text here. Machine learning is fascinating. It's a string of text. That's why it's in quotation here. Now, for tokenization, what tokenization does is to break down this sentence here, this text here, into its individual words. Machine learning is fascinating. We have broken it down into 4 places. That's what tokenization really is. For bag of words is just telling us, is just going to be showing us the frequency of each of the word. Machine appeared once, learning appeared once, is appeared once, and fascinating appeared once. Why this term frequency, inverse document frequency, is a more complicated one. It looks at the frequency of the term and it's multiplied by the log of something related to the distribution of each word relative to the entire document. So it has a very funny formula. And this is what it just tells us. It just tells us the relative importance of each word as it is related to the entire data set. So now we can see fascinating looks like it's quite important. That's why it's having 0.8. Machine and learning looks like they are equally important. That's why it's having 0.5. While is has a low importance. That's why it's having 0.2. So by converting all these raw text into numerical feature, the computer will be able to analyze and learn from the data effectively. So featureization is a very critical step for our machine learning pipeline, bridging the gap between raw data and actionable insights. So it's very important for us to really understand how this featureization takes place. So we are going to be talking about the data collection, which I briefly mentioned in the last class. So I'll just mention this again. So the first step is to get the raw data. The raw data can come from sensors database, data entry by the human, or the internet. It can also be in different formats like text, images, audio recording, or video. So the quality and the quantity of the data collected are very, very critical as they are directly impact the performance of the machine learning. And there are different sources of data too. You can get it from your sensor, like your smartwatch, your camera, your microphone. You can get it from that. You can also get it from a database, structured collection of data such as SQL database or data warehouse that stores information in a tabular format. You can also get it from API, application programming interface, that allows you to access a data that is in another place, such as the cloud, or maybe social media feed, or weather data or financial data. Web scraping is an automated method for extracting data from a website. It can also be manually entered too. Probably, maybe you've shared out some questionnaires to people, and you need them to input the answer, to write down their answer in those questionnaires. So obviously you are going to use a manual entry for this kind of data collection if it's small, or if it's a specialized information that cannot be collected through the other method. And as you all know, we have different type of data also that can be collected. Text, which is the most popular type of data, which is a written information. There's a image data, there's a audio data, there's a video data, and categorical data such as color, name, product type, and demographic information. So there are some things that we need to consider when we are collecting data. Number one, we need to consider the relevance of the data we are collecting. That is it really relevant to the problem you are trying to solve, or the question that you are trying to ask, the question that you're trying to answer. The quality of the data too. Is it accurate, complete, and reliable? Because poor data will lead to misleading results. The quantity of the data, we also need to collect adequate amounts of data that is required by our machine to actually pick up the points and pick up the things that is actually going on within our data sets. That's to determine the quantity. You can also use some sampling method. There are some formulas that you use to calculate sampling method. Usually for an infinite amount of population, the required sample to collect is usually 385. You also need to consider the ethics and the privacy. That is the privacy of the individuals from which you are collecting data from. Do they give you the permission to use that data? And also you have to anonymize the sensitive information there, so that if somebody ever gets access to that data, they will not be able to trace the location or who that individual is for that particular data point. That's what anonymizing is all about. Now, in order to make our data very, very of high quality, we need to clean the data. Once you've collected it, the next crucial step is to clean it. This involves preparing the data by removing or correcting any inaccuracy, inconsistency, or irrelevant parts that to ensure that the data set is of high quality. Clean data is essential for building reliable and accurate machine learning model. So what are the steps? You need to handle the missing data, the data that are not there. So if you have, like, let's say you have about 3,000 data points, and five data points there are having a lot of missing value. So what will be the impact of removing just 5 data points out of the 3,000 that you have? You need to actually calculate it. Well, what percentage does that 5 represent out of 3,000? And is it going to have so much impact on the accuracy or the performance of your machine learning model? If it's not going to really affect it that much, then you can remove it. If it's having too much of missing data that you cannot fill in properly. There's also imputation. You can also impute the missing value from it by using a measure of central tendencies. The measure of central tendencies involved the mean, the median, and the mode. The mean just means the average. You add everything together and you divide it by the total number of data points. The median just means the middleman. That is, when you arrange the data from the lowest to the highest, you pick the one that is at the center of it. That is the median. And if there's an even number of data, you add the 2 that is at the center and you divide it by 2 to get the median. The mode is just for the one of the highest frequency, the ones that has the highest frequency. So either of these 3 that you choose to select now depends on the data set itself. It depends on the feature that you're trying to apply that measure of central tendency to. And you can also use other sophisticated methods too, like k-nearest mean or even regression, to fill in the missing value in your data sets. And you can also remove duplicates from it. You can use the pandas library to remove duplicates if you are working with CSV file or JSON files. You can also use Excel too, Excel software, to remove duplicates. It's there. There's a option there to remove duplicates on Excel. Excel will look for any rows that is duplicated and remove it for you if you ask it to. And you can also correct inconsistency, like probably the date format. Maybe the date is starting with year, then month, then day, and some of the date format is year, day, and month. Obviously, there's a problem somewhere with that data. There are 2 options. The first option is for you to go and meet the data custodian. The data custodian is the person that has that data, the person that is responsible for that data set itself. You can meet the data custodian and inform him of the inconsistencies that are there. So the custodian is going to let you know why those inconsistencies exist and will give you a clue on what to do to correct it. Irregular capitalization can also be there, or even wrong unit measurements can be there. And there might also be some obvious errors too that could be there, such as a typo or mislabeling. You also need to filter out outliers. Now, what are outliers? Outliers are those data that are very, very far away from the trends of data sets. In when you plot your graph and you see it, you will notice that if all of the data are within a certain range, let me share this window. Now let's say this is our, let me zoom into this. Okay, good. So this is our graph here, plotting our data set. Now, let's say there's a particular data that is somewhere here, for instance, and there's another one that is here. Hello?
The screen is not showing. The screen is not showing.
Oh, this screen is not
You can't see
showing
your screen, sir.
at
Yeah.
all.
Yes, the example,
I'm
the
coming.
illustration you're trying to show us.
At all, at
Okay,
all,
okay,
it's
okay,
not
okay.
showing.
Okay, what about now?
It's showing now. It's
What
showing
about
now.
now?
It's
Okay,
showing
good.
now.
So now this is,
No,
yes.
I
So
can't
this
see
is
it.
the
I can't see
plots.
it.
Now, can you see it now?
Yes, we can see now.
Good, good. So now this is the plot of our data sets. All these black dots here, they are the data sets. Now, obviously, if you look at this data that is here, this one and this one, they are outliers because they are very far away from the usual trend that is common to most of the data points. So these are outliers. So we cannot include this outlier in our analysis because it's going to cause the machine to have a wrong line of regression. If you decide to include these two outliers, probably our line of regression is going to look something like this. It will look something like this because it's trying to consider these two outliers that are there, and this line is not going to fit most of the data points, but it will just shift this regression line in a wrong direction. So it is very important for us to really plot our graphs and able to pick out the ones that are very, very far away from the usual trend of data. So let's go back to the slide.
Thank you so much for this
Good.
explanation.
All right. So now you understand how filtering outlier does. Now we also need to undo irrelevant data. If there's any data that doesn't contribute to the analysis, like what I showed you the previous time, for instance, talking about the name of the person, that might not contribute anything to the analysis. The name of someone might not tell us anything about the question we're trying to answer or the problem we're trying to solve. So this is an irrelevant data that does not need to be loaded in the machine learning. Now, for normalization and standardization, which I've already explained, have I? No, I don't think I have. Have I explained normalization and standardization?
You've explained it before.
Okay, yes, I've explained this before. Good. So normalization is just putting the value between 0 and 1, while standardization is putting the value between 3 or 1 or 2 standard deviation, depending on your data set itself. So it can range from -3 to +3. That value is representing the standard deviation. That's why they call it standardization. And encoding categorical, you already know how to encode categorical, either using one-hot encoding or label encoding that is suitable for the machine learning algorithm. And there are different tools that you can, like I said, pandas too. You can use pandas for data cleaning and manipulation, and then NumPy for numerical operation in Python. Usually they use it together with pandas. So this is just an example of handling missing data. You can decide to undo this. For instance, Jane here now, this is a role. Yeah, it doesn't have any data for age. That's why there's just comma, and there's nothing between it because age is missing there. You can decide to find the mean of all the age and assign Jane as the mean. The mean is just a value that can represent all other values, just the average value that can represent all other values that may be missing there, to fill in the missing age for Jane. And to remove duplicates, if you notice that John here and John here, they are perfectly duplicated, so we can remove that duplicate also. There's a method in pandas too that's used for removing duplicates, and there's also a method in Excel too we can use for removing duplicates. You correct inconsistency to ensure that formatting is done correctly, regular capitalization is corrected, and all that. So this is under data transformation, as you said. So over here, we're going to see how this the examples that I've given in this Python code. So before we start looking at the code, I would like to ask if there are any questions at this point now. There are no questions at this point.
I have questions, sir.
Please, sir, I have a question,
Okay.
sir.
Okay, you can ask now.
Okay. You just talked about categorization, if I'm not mistaken, with one auth encoding or label encoder. Is it is it compulsory we have to categorize our data? Please kindly drill into that a little bit.
Okay. We are not categorizing our data. What categorical data means is that it's not number. It is not a numerical value that you are finding in the feature. Like, let's say under gender. Gender is a categorical data, male and female. That's what we mean by categorical. So we need to encode this categorical data, male and female, because you cannot just pass male and female to a machine because the machine does not understand English. You need to convert male and female to the format that a machine can understand using one auth encoding or label encoding, as the case may be. One auth encoding can be 0, 1 or 1, 0. While label encoding can be 0 for male and 1 for female. In this format, the machine will be able to differentiate male and differentiate female. As humans, we can just tell a human male, female, and a human will understand what you're saying. But you can't tell a computer male or female. The computer will not understand you unless you convert it using one auth encoding or label encoding. So that is what this category encoding categorical data means.
Thank you very much,
I've been able to clear the confusion.
Yes,
okay.
sir. Thank you, sir.
Oh, okay, good.
Okay, that's mine.
Okay, so now let's move on to the next part of it. Now, so this is a Python code right now. So over here, we are trying to use bag of words. We are trying to use bag of words now to count the frequency of each. Now, look at this text here. This text here is having two different sentences. So this text here is going to be our data set containing two sentences. The first sentence is saying, I love machine learning. The second sentence is saying, machine learning is fun. So we are trying to use bag of words now to make the computer understand this, I love machine learning, and machine learning is fun. So what happens when you run this code? What is it going to do? It's going to actually break. There are a lot of things that are working in the background. A lot of things are working in the background. It's going to tokenize it. It's going to break it into its individual words, tokens. That's what is going to happen the first instance. And then by the time you print it, X to Harry, this is what you're going to have. And by the time you get the feature names out, this is what you're going to have. So what this means is that in the first sentence, it's trying to tell us the frequency of each word in this feature here. Fun is learning, love, machine. So it has actually broken it down into all of its token without repeating anything. That's what tokenization is all about. So for the first sentence, it's trying to tell us that fun appeared 0 times, which is true. For this first sentence, there's no fun there. Is also appeared 0 times, which is true. There's no is there. Learning appeared once, which is true. Learning appeared once. And love appeared once. Love, I love machine learning. Love appeared once in the first sentence. Machine also appeared once, which is true. Machine appeared once here. Now, for the second sentence also, is trying to see fun. How many times was fun appeared? Once, which is true. Fun appeared once. Is appeared once, yes. Learning appeared once, yes. Love does not appear. That's why you have 0 here. Love is not here. Then machine appeared once, which is true. So this way, this is a format that the machine is going to use to understand what each of these to actually represent each of these words in it, considering our data set called the text. So now this one is the term frequency inverse document frequency. It's just measuring the importance of a word in a document relative to the collection of documents, especially when we have a lot of sentences there and a lot of data sets there. So it's going to be comparing each word. That way, the machine will be able to see relationship between different words in a way that is very peculiar to a machine that humans can't totally comprehend. So this is what is happening in this case.
Pardon, sir. Please,
You can see.
that bag of words, sir. Please, I was actually
Yes.
wondering why I did not feature in that font.
I. Oh, for high, right? Oh, yes. Now, very good. Very good question. Now, for this I here is a stop word. I is a stop word. Is actually, it makes it so because of the rate at which I occurs is going to is like, it's just like having an outlier. It's like a, how do I call it? It's like a joker card, something that appears a lot of times. Those are stop words. Stop words are words that like really appear very frequently naturally in sentences. So it's a feature that has been built into it on its own. It has been built into this count vectorizer. The count vectorizer, it does means bag of words. It has been built into it to eliminate stop words such as I, an, like an, a. Those are the words that doesn't really say so much, doesn't really give us importance. Remember I said something about featureization. You remove irrelevant features. So you can look at that I as something that is not really relevant like that to actually help the machine to understand relationship between words. I hope I've been able to answer the question.
Thank you very much, sir. Yes, sir.
All right. Okay. So moving on. So this term inverse frequency, term frequency inverse document frequency can be a very long word, and someone can actually mistake where you're actually pronouncing it. That's what is TFID. That's what it means. It's just looking at the importance of it in each word, the importance of 1, 2, 3, 4, 5. 1, 2, 3, 4. It's just looking at the importance of each word as it's related to the entire word. Like now, you can see the same thing happened there too. Fun is learning, love, machine. It's trying to look at the importance of each word as it is related to the particular sentence. That's it. So it's like comparing each word, like fun now, for instance, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Fun now is being assigned a value as 0 here for this first sentence. Is not there. So it's getting 0 as its value. Is too is also not there. So is here is getting 0 as its own value. Learning is there. Learning is being assigned an importance of 0.5. Love is being assigned an importance of 0.7. You can see that love seems to be like an important word here in this sentence. Why the machine is assigned the value 0.5 here for the first sentence. For the second sentence too, the same thing happens. Fun is assigned the value 0.57. Is assigned the value 0.57 also. Learning is assigned the value 0.4 in this case. Love is assigned 0 because love is not even there at all in this sentence. Why machine is assigned the value 0.4. That's how important it is in this particular sentence. So that's what term frequency inverse document frequency is all about. Now we can move on to word embedding. There are different advanced methods for word embedding. Like you have a question, okay? You can go on.
How does the machine, the method the machine uses in assigning those? What is the method the machine uses in assigning those values to particular strings?
Yes, the method is term frequency inverse document frequency. That is the technique that is used to assign it. Is a formula, is a mathematical formula for calculating it. There's a formula for it. It's using mathematics to calculate all these values. The mathematics is term frequency multiplied by the inverse document frequency. Term frequency has a formula. The inverse document frequency has a formula too that has logarithm in it. When you multiply these two things together, you are going to have each of these values that you are seeing here. So it is a mathematical formula for it. And this technique is known as the term frequency inverse document frequency. So a computer will calculate everything quickly for us and give us the value. So that's how we're going to know the importance of each of these featurized words in the sentence, in the two sentences here. I hope I've been able to answer that question.
Yes.
All right. So now there's word embedding advanced method like what vet globe representing words in a continuous vector space. I mentioned something about continuous vector space the last time, like a higher dimensional space, how each of these words are actually represented in a high dimensional state. Now look at this machine now. In these sentences that we have, I love machine learning, and machine learning is fun. We want to print out the word vector, WV, for machine. This is the representation of the word vector for machine. So obviously, if you count these numbers, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, meaning that there are 10 features here. That is, this is like, you can look at it as being in a 10 by 1, in a 1 times 10 dimension. That's what it means. And these are all of the features that are being used to represent the word machine.
Kindly come
So
again, sir, please.
Now, if you count all of these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 numbers here. They all represent the word machine. This is a continuous vector space. A vector has magnitude and direction. So each of these numbers are the weight. You can look at it as the weight of the 10 features that represent the word machine. So whenever you're sending the word machine to a computer, this is what it's going to see. This is how it's going to see it. So this is a way of representing it. You know that if you don't understand, right? You know, in the English word, there are over 100,000 English words. So we have to look for a method to represent each of these words in a way that the machine can actually understand and work with and calculate with. So this is the method that is most convenient for the machine to actually understand the word machine. So all of this word can be represented by different. So let's print out another word now. For instance, let me print out another word. So this is for machine. For another word, like let's say learning. Learning. Let's run this code here for learning. Now look at this. We have two different vectors now. Two different vectors here. This first one is for machine. This second one here is for learning. So now when the machine is not trying, if the machine is trying to compare machine to learning, it is this vector space that is going to be looking at. For the first feature, you can see this is minus 0.09. This one is minus 0.005. It's very dissimilar. It's very far away from each other. For the second feature, 0.05, this one is 0.002. It's also very far away from it. For the third feature, 0.08, this one is 0.05. It's a little bit close, so there are some similarities there. This one is 0.04. This is 0.09. It's kind of far away. This one is very, very far. This two is also very, very far away. This is okay. This one is very, very close. You can see that at the 1, 2, 3, 4, 5, 6, 7. At the 7th feature, we are beginning to see how the word machine is similar to what? To learning. So an example of the application of this, and also for this feature to 0.09, 0.08, they're very close to each other. 0.049, 0.052 are very close to each other in terms of the numerical value. 0.09, 0.03, that's still kind of far away from each other. So in this feature here, this feature, and this feature, the word machine and learning are very, very related to each other, coming from our sentences data set. So this way, the machine will be able to know the relationship between machine and learning. So that's what this continuous vector space is all about. It's just trying to show us how machine and learning can be related to each other using the continuous vector space.
Please, sir.
I hope I've been able to answer.
Hello, sir.
I'm coming. Okay.
Hello.
I
Yes,
hope
sir.
I've been able to clear the confusion in that aspect.
There is one more question I have, please, sir.
Is it
Can you hear
related
me?
to this, or is it related to this word vector, this continuous vector space?
Yes. Please, I'm
Okay,
lost.
it's related to it. Okay.
I don't actually
Okay.
know where we get the vector size 10. I could
The
see that you
what?
are the vector size, which is 10. How did the machine arrive? Is it that it's inputted? Is it that there's something is imported from somewhere, or what?
Okay. No. These ones are just these are arguments. These are just arguments for this word to vector method. These things are arguments. What it means that this word to vector is taking this sentence as an argument, is taking vector size 10 as an argument, is taking Windows 2 as an argument, is taking minimum count 1 as an argument, and the workers equals 4 as an argument. They are just parameters that this word to vector needs. They are the things that you need to actually assign to it in order to actually vectorize it, to present this thing in a word vector.
All right, it's clear.
That's what it means. So the vector size, just what we're seeing here. 2, 3, 4, 5, 6, 7, 8, 9, 10.
The outcome of this?
What do you say?
Maybe we should
Does
change it, see whether it's going to affect the output.
Oh yeah, sure, definitely. Like, you want to change it, Abi?
no, the casing
Yes,
of
sir.
That we should
the
change it.
upper casing
It
and
will.
lower casing and stuff like that of the machine and the
I'm
learning.
coming. Let's try it. Oh, like, oh, you're trying to see if there's a difference between upper and lower case.
Yes, sir.
Oh yeah, there's really no okay, that's a very good question. Let's try that. Let's try that and see. Let's see if it can differentiate, if there's a difference between the upper and the lower case for machine. Now let's look at it. So you see that it's actually different, although it's going to be similar in so many aspects. So he's considering it as a different thing. Now, the reason for this is because Python is a case-sensitive programming language. It's very case-sensitive. So machine with a capital M, machine with a small m is considered different. So let's look at the similarities. You can see it's a little bit similar at the first vector. The second is very far away. The third one is very similar, 0.08, 0.09. No, it's not similar, it's different. You need to consider this negative value too. Okay, it's a little bit far away from here. It's far away in this particular feature. It's far away in this feature. Yeah, it's very similar. Okay, it's still far away because negative here. Over here too is also different, is the similar here. So obviously this data set that we have here is very, very small. So there's no really much information for the machine to really tell relationship between words in sentence. Let's say we have a very huge data set, like our sentences now, we have like 1,000 or let's say 10,000 sentences in it that we are trying to use to train our machine. If you run all of this now, you will see that you begin to appreciate the importance of this continuous vector space. For this, if there are lots of sentences that are in this sentences lists, yeah, this is a list. In this sentences list, you'll be able to see how one word is related to another word. You'll be able to appreciate it better that way. It's possible because they are in a different list, because this is a list. This is a list inside a list. You understand? Because they're in a different list. That's why it's seeing this capital M machine and a small m machine as very, very different from each other. So this is just to explain how a machine understands human text, how a machine understands, how a machine interprets, and how a machine actually manipulates words that may be present in your training set that are not numbers. So I hope I've been able to explain what is going on with this continuous vector space. Is there any confusion with that, the continuous vector space? Okay, having none, we'll move on to the next slide. So this is also another example, looking at machine and learning too. It also does the same thing. It also kind of like compares each of these feature 1, feature 2, feature 3. I'm just giving an example. If you are trying to compare the two, just to make you understand what this continuous vector space is all about. Yeah, I'm using machine and learning. I'm not using king and queen here. The reason why I'm not using king and queen, because king and queen is not in our original sentence here, so it's not going to work here. It's going to throw us an error. There's probably a key error. So now this is for image data. Image data too can also be converted to numerical matrix. In this case, we use a convolutional neural network for extracting features from an image. So for the image part, you state what the image part is, and then you load your image. So this TensorFlow is just a library. It's a library for deep learning. So it's very powerful for image processing. It's very powerful for image processing. So now this is an example of this. This is an example of image. This elephant.jpg. I've already uploaded the elephant.jpg in this our workload. It's just a picture of an elephant that is there. This is it here. It's a picture of an elephant there. So if we run this, if we run this particular code now, it will just print out the feature shape for us, 177512. This is the feature shape for us that it prints out. And this VGG16 that you are seeing here is just a model, is a machine learning model that is used for classifying images. That's the whole point of it. It's used for classifying images. I'm coming. Just a minute. Okay, so now for this elephant.jpg, if I should decide to run this now, it will bring out this feature. But let me remove all this. Let's remove all of this commenting. I commented out everything. Let me put this back since it's not part of the code. So let's run this. So this is going to predict what this elephant.jpg is all about. So let's run this and see. Okay. Oh, it looks like our time is up. I've spent over 1 hour. So in our next class, we are going to come back to this and we will explore this further from our next class. That will be on Monday. So thank you so much for attending this webinar. I would like to know if there are any other questions at this point. Our time is up already. So let's just spend probably the next 5 minutes to see if there are any questions to be asked, if there are any confusions right now. So Atilade's hand is up. Atilade, you can ask your question.
Thank you, sir. Hello, can you hear me?
Yes, I can hear you.
The question was actually when we it's from when we started the class, when you talked about data cleaning and you talked about removing of duplicates.
Yes.
So I want to ask, we apply to, when you use experimental design, you can input replicates, and then when you replicate, you are not going to replicate the whole of the data set. So does it apply to that kind of data when you have the design points being replicated, or is just when they are exactly the same?
No, I didn't mention replication. I said duplication. Like if you have a data that is I'm coming, for instance, if you have repeated data duplicates, when we have repeated data, for instance, in this data set, if you have a repeated data like this is a data point here. Let me copy and insert. Let me insert it somewhere here. If you have a repeated data, we have to remove it because it's just like, how do I put it? It's just like having the same information twice. It does not really help the machine it doesn't actually give any new information to the machine. So we have to actually remove that duplicate from it. In this case now, I've made a duplicate. This data set does not have any duplicate, so I artificially created a duplicate. So you have to remove a duplicate from it. So you can see this is Excel. In this Excel, you can there's a feature there for removing duplicates. If as you click on this remove duplicates now, it lets me know if that you can see now one duplicate value found and removed. So the others, the over 50,000 unique values remains. So we have to remove duplicates that are there. So it's an error. It's like an error in the data set. It has to be removed from it, because if you are just having duplicate, it doesn't give the machine any new information. That's the reason why we need to remove that duplicate. So I actually did not recall mentioning replication. Replication just means like just repeating something. I hope I've been able to answer that question.
I'm satisfied.
Huh?
Yes, I'm okay. Thank you very much.
Okay. So in the next class, hopefully we'll be able to move faster than this and talk about the remaining part of the lecture. So thank you very much for attending this class.
Thank you, sir.
You're welcome.
Thank you very much. I really appreciate that.
Yeah, no problem. You're welcome.